So when Ollie asked me to come over, as he did that many times, I was always a bit worried about the heat in Sydney and environment, but he convinced me that it's not always that bad. So I'm here now. So yes, the UTCI, that's the topic Ollie gave me, and it's an interesting one that you get given a topic, talk about this, and not the other topics I wanted really to talk about. But it doesn't mean that I think it's not a good topic. I guess the reason I was a bit hesitant is that we developed the UCI probably about 15 years ago. And since then, I've been working also a lot in other areas where we use the UTCI, but have not really investigated the UTCI itself in terms of further validation, etc. But I'll try to summarize the developments, because I think when I look at some of the literature, you often see that people don't really understand the choices that were made when we developed the UTCI. And that's really important to consider, because this was obviously a big team effort. I'll show team members later on. But when you develop something like this, along the way you make a lot of choices. You have to make a lot of choices. And when people just pick it and use it without thinking about those choices, you might use it in the wrong way. So let's kick off. I should point out, I put a second author there, and that's Peter Brode, who has been really important in the development of UTCI, but also over the years we've been exchanging some of the slides, etc. So some of the slides I've adapted from his his work as well. So going back to the early days, we looked at key applications of climate indices, and this was the list that we really came up with in the early days. So we have daily forecasts, the weather service, like in Canada, etc. They talk about the wind chill in the weather forecast. The idea is, would we have something which would work across the range? Public health systems, heat health warning systems, they are really in need of a good way to describe or capture different types of heat. Cold stress, like I said, that's an example. And often giving advice is really important, which can be just, there's some apps now that advise you what to wear today, which is really good. What kind of outdoor activities you can do, and how much water you need to take. And especially in relation to Ollie's work with the tennis here, sport heat risk or sport health risk is an important one to when they have to decide whether they can let an event go ahead, a marathon, etc. People need guidance. And then meteorologists and climatologists do lots of other stuff with climate indices, bioclimatological assessments, mapping, country mapping, etc. Urban design, so indoor and outdoor design of shaded places, for example. They need something to show whether things have improved or not, pre and post, how you can measure that. Consultancy for where to live. A long time ago, I wrote an intro to a book which was about the United States and just describes all the climates across and how livable the area would be, mainly for retirees, I think. Outdoor recreation, epidemiology, really important, of course, and especially in the context of the center here. Climate impact research. What do we expect for the future? So when we started looking at this, why do we need UTCI? So when we started this, it was really the question, why another one? And what if I say another one? If you look at some of the reviews, I did a review 2016 and discussed a number of these, but there's further reviews by De Freitas and Ioannou. There's more than 300 thermal indices if you dig in the literature. Some have been published once and then disappeared immediately. Some gained some traction, etc. Some gained traction in different parts of the world. So if there's 300 there, why do you need another one? So that's what I really want to talk about in the beginning, in the first part. So we have loads of those. Now the first problem is that many of these indices, and for example, ambient temperature is a climate index in itself. So many of these indices only use one or two parameters. So maybe just ambient temperature, which we know and we'll see later is not a very good descriptor of the climate. Others, ambient temperature and humidity, that improves things a lot, but of course doesn't consider wind, doesn't consider radiation, and humidity, relative humidity, vapor pressure, etc. So they just cannot capture all climate influences if they only use a part of the four main climate parameters. Most of these indices are based on physical instruments measuring climate parameters. So measuring ambient temperature, measuring globe temperature for radiation, or radiometer, or other ways of measuring radiation. Relative humidity can be measured as relative humidity. Dew point temperature reflects temperature and relative humidity. Or in this wet bulb temperature, which can be natural or psychrometric, one of the important sources of confusion with climate indices in the past, that people mix these two up, and we'll talk about that later. And air movement, of course. And we wanted to develop, the suggestion was the universal thermal climate index, which would go from extreme cold to extreme heat. Probably a bit ambitious, but there you go. And most of these only cover part of the climate range, so it's either a cold index or a heat index. So going over some of the simple climate indices, what's the principle of most of them? I've shown three here. So this is just a thermometer and a relative humidity, and where it crosses, it gives you with colors indications of issues. Very few will know this. This is what we call a Botts ball, which is a black globe which has a cotton gauze around it that you can make wet, so it becomes a black wet bulb. And then you have a dial up here. The most well-known one probably is WBGT, the wet bulb globe temperature. And that has three sensors: air temperature, which is covered here or protected from radiation; a black globe, in this case quite a small one, which is sensitive to radiation, but also to wind, because if it heats up and you blow wind over it, it cools it down. So that's, again, what people tend to forget when they replace this with other things. And the really important one, which is the most important factor, accounts for 70% of the value, the natural wet bulb temperature. So what's a natural wet bulb? It's, in this case, we have a reservoir here, a water reservoir, a thermometer, electronic thermometer here, and a cotton gauze around it, which is wet. So natural means you just put it there and you expose it to the environment. So that means if there's sunshine on it, it will have a little bit of an effect, but because it's white, not so much. But it will be, of course, affected by relative humidity, because the moisture will start to evaporate from this cotton gauze and cool this sensor. And if you blow wind over it, it will strengthen the cooling, so it will drop further. And just to jump ahead a bit, one mistake people make, because they don't always have this value, because it's actually a complicated one. It's an easy one to measure with the instrument, but a complicated one to calculate if you don't have the original instrument, is people take other measures instead of this natural wet bulb. For example, the psychrometric wet bulb, which is a similar sensor, but now you have a fan sucking or blowing air over it, so you fix the airspeed. And that means that sensor tells you something about relative humidity, but not about the wind speed that might be cooling you down or heating you up in the location. So the measuring device, for example, WBGT, is influenced by temperature, humidity, air movement, and radiation in the ideal case. And then you get a value. In this case, these are weighted outside by 0.2, 0.7, and 0.1. And you get a climate index like the WBGT. And then you can go to a table and look up the expected heat strain or heat stress related to that value. So potential issues, I'll put the reminder in. So use of incorrect sensor type, or not measuring all parameters, often only temperature and humidity. And as I said, the psychrometric wet bulb is not a good replacement for the natural wet bulb. So what is the issue with WBGT and many others? The first is they do not always capture human response and human heat exchange accurately across the range of conditions. They've done a really good job. WBGT has been around since the 1950s and has helped a lot in reducing heat illness in the military, for example. So it's a really good tool, but there are some issues. A simple one, for example, relative humidity. If you have this sensor, whether it's the natural or psychrometric wet bulb, it might show you 100%. And what the difference is between the instrument and a human. If the environment is 15 degrees, 100%, we can still evaporate sweat, no problem at all, because the vapor pressure on the skin is higher than the vapor pressure in the environment. So that's one of the things that sometimes can go wrong. Then things like effect of wind at extreme temperature, I'll show that later on. So if we take one step up, so if you, for example, look at ISO standards, WBHD is an ISO standard, and one step up, the idea was to use heat balance standards or heat balance models, heat budget models. The predicted heat strain, predicted mean vote, and required clothing insulation are examples of these. Are they better? And yes, they are better because you consider a lot more factors in it. So I'm not sure you're familiar with the heat balance. I'll jump through this quite quickly. So I have this chap here is doing some work, and because of the work or because of living in general is generating heat, metabolic heat. And if there would be no heat loss, the person would warm up. So we need to lose the heat, which you can lose by conduction, by convection of air around us. Sweat evaporation is a really important. The air we breathe in is usually cooler than we breathe out and usually drier than we breathe out. And then you have infrared radiation from the environment. You could have sunshine and reflected radiation. So there's a lot of different ways you can lose heat, but also gain heat. Especially solar radiation, of course, we tend to gain heat rather than lose heat. So if you capture this in the heat balance equation, you can calculate or estimate, will this person in this climate cool down or warm up? And clothing is an important factor because that's an interface between your skin and the environment. So you calculate the heat balance equation. It's a really good tool to model things. If you're going to do an experiment by first putting things into the heat balance, making estimates of the heat exchanges, often you find that you might have to choose different conditions if you want to show the effect that you're looking for. So a similar approach, we've got the heat balance model. We measure individually all these different factors, metabolic rate, temperature, humidity, air movement, radiation, and clothing. You push them into the heat balance. You get an outcome, which might be a cooling or a heating rate. You check it for a reference value, which could be different for acclimatized people. This is actually for the WBHD, that's different for wind, but definitely different for different clothing. And it tells you what the expected thermal stress is. Bit of a question whether that's stress or strain in this case. So if it's body temperature, like a predicted heat strain, it's more pointing towards strain. These identify stress. I deliberately called it stress in this case, but do not always identify thermal strain of the human body related to interactions between physiological reactions, for example, changing skin temperature, because that's fixed in these models, sweating distribution, where is the sweat coming out of the skin, and are all parts, it assumes usually that all parts of the body are wet with sweat, maximum sweat rate changes with wet skin, hydromyosis, and the link of those with heat loss and gain. So there's still something missing, but this was already a big improvement compared to the simple instruments that are available. So when we started this process of UTCI, we had simple indices, heat balance, where we said, yes, much better, but probably not the best yet. And then the final one, could we use a human physiological model to indicate heat load and heat strain? So that was the question at the start of UTCI. So how would a physiological model look like? In this case, a computer model. So this is one that I worked on myself for my PhD a long time ago. So you have the environment, just like in the previous slide, and there's a heat exchange with the skin. So you can do that. Again, convection, conduction, evaporation, etc. You've got a skin layer, you've got a body core, and you've got heat exchange between the two. And then, depending on what kind of model you look at, you send these signals to the brain. You might have a skin temperature threshold for action, a core temperature threshold for action, and they are then sent to the effector responses. And one is skin blood flow, and very simplistic. If it's cold on this side, hot on that side, or if the body temperature is too high, you go to the right. If it's too low, to the left. So if it's too low, you vasoconstrict and constrict all the blood flow. If the body temperature is too high, you increase the blood flow to the skin so you can lose heat from the skin. Same thing for sweating, much simpler. If you're cold, it's unusual to sweat, but once you get warm and too warm, you start to sweat and sweat more. Shivering, the mirror image of this, and behavior, which is of course not really often used in these types of models for applications, is our biggest thermoregulatory control mechanism. Putting on clothing, taking off clothing, moving, switching on air conditioning, etc., etc. but in a total model that would be part of the system. So to put that in the context of UTCI in terms of the history, and I've been around a long time, as you obviously already guessed. Around 2002, the International Society of Biometeorology recognized the need for a universal climate index and initiated work by its Commission 6. I'm not sure, Richard, were you involved at that time already? Yeah. And then we had, because that was a very slow progress, because there's a lot of work would have to be done, and of course nobody's paid. So then we had the luck that we've got funding from the European Union in a cost action. And the interesting thing about a cost action, it funds to bring scientists together. It doesn't fund any research. And when I go through this and I look back at this, it's amazing how much work everybody has done for this without getting money for the research, because people really were interested and wanted to do it. And it was work performed under the World Meteorological Organization Commission on Climatology. So just to indicate a couple of people, this is Gert Jendritsky. I would say that's the father of UTCI. That's really the person who had the initiative and pushed very hard for it. So he was the chairman. I was very pleased to be allowed to co-chair and chaired working group 1, which was thermophysiological modeling. Philip Weiss looked at meteorological data and environmental input data. So if you have satellite data, how could you use them in a system like this? And then Ekaterina Bachvarova from Bulgaria was looking at applications. But this is the list of people. I'm not 100% sure it's complete, but it comes from the official report. And again, Richard, you're on that list. Obviously, you're down here. But so lots of people came together. The fact that there was money for travel was, of course, very attractive as well for researchers, and especially we had a lot of Eastern European researchers who used this as a way of learning from the other researchers, and that was a really important part of the project. So this was the requirements that were set out before we started. The UTCI must meet the requirements that each specific value of an index must result in the same thermophysiological effect, regardless of the combinations of meteorological and other environmental input values. So once you have a value, let's say 50 or whatever it is, of that has to be linked to a specific response of the body. And we'll come later on, that's not a simple single parameter response, but a combined response. So that was a really important one, because if you don't have that, you can't link the index with specific situations, because you could have multiple solutions to it. Thermophysiologically responsive to all modes of heat exchange. So it has to consider wind, humidity, temperature, and radiation. Applicable for whole body calculations, which is the most important application, but ideally also for local skin cooling, like frostbite. So in the cold, you should be able to get information about frostbite risk as well. I think that's one thing which went into the background slowly during the project, but might be picked up. It should be possible with the model, but it wasn't the focus towards the end. And it's a universal climate index, so valid in all climates, seasons, and time and spatial scales. So that was the plan. Appropriate for key applications in human biometeorology. So let's go through the steps of the development, because like I said, it's probably important for you to just see this once and know if I apply it in a certain way, does that meet with the way it's actually developed? And the first one is a thermophysiological model. Which one are you going to pick? Compare and validate existing physiological models. So these were the models that were tested. Some of them were quite basic, so that would only work for the cold. But there's quite a number of models that you see here that actually went and were compared. So the first thing we did actually was collect a big database of heat exposures, cold exposures, and Agnes Psykuta from Switzerland actually did all this comparative work. So you want to take the best model based on performance and validity. So extensive comparison to collect a database. And just to go back, I guess, very quickly, most well-known models, for example, if you go into building, I think Tanabe model at the time was quite, well, Richard is involved here with the outdoor standard effective temperature. The Berkeley model is quite well-known. So there's a number of models that were possible to use. Now, if you pick a model, there are things you don't expect. So once we were working on this, suddenly issues came up. Is it available? A lot of these models are, how do you say that? The people are living because they work on the model. They earn money using the models and selling consultancy with those models. So surely they're not going to give you the models. Yeah? That was a big problem. So copyright ownership. Thoughts about, does it have to be an open access model, or do we just close the model? And open access models, open source, pros and cons. What you see with some of the models here is that PhD students all over the world that start to model, pick one of those models and develop it in a direction. And somebody else develops it in this direction, but hardly ever somebody brings these all together. So there's a combined improvement of all of these things. If you create like a standard, like the ISO standards, and UTCI could be an ISO standard, or in general, if you create something that's going to be used across the world, you have to be sure that people use the same model. So open source, big problem would be you get lots of developments, which will be really good in some ways, but when people then calculate the UTCI, that could be a totally different UTCI from the original model. So that's why it was decided to lock the model down. And that also helped because the model that was chosen, which in the end was the Fiala model, it didn't take away the opportunity for Dusan Fiala to continue doing consultancy in it, because people couldn't go straight into the actual model. So this is the validation work that I mentioned by Agnes Psikuta. So chosen was the Fiala model. So this is the passive system. You've got lots of different segments. Each body part has a skin, inner skin, fat, muscle, and bone compartments. There's blood vessels in there as well. And you see you would have 2 feet, obviously 2 lower legs, 2 upper legs, upper arms, etc. Because this was not about direction, so originally you can use the model in directional applications in a car. One side is to the window, the other side is to the inside of the car. That's all irrelevant here. So the model was modified and it was brought down from 19 to 12 compartments, so with left-right symmetry. And that brought down the nodes, the different sections that are in here, from 342 to 187 nodes. Background with that is you can't afford for this to calculate for 20 minutes to get you one value, because these people want to calculate it for the whole world in 10-kilometer grids, the meteorologists, so it needs to be very, very fast. Now, later we'll talk about how we achieve that. Then you have the active system, just like the example I gave before, shivering, skin blood flow, Q10 effects of metabolic rate, sweating, etc. So that's the basis of the model, and there's a lot of literature on this. So verification and validation of the model, and that then generated the UTC index model. And like I said, that was in end a locked down black box, yeah, when we finished with that phase. So what you get now is you have this black box model here. Again, you measure all the different, or estimate all these different factors. This generates the physiological response, so physiological heat strain response, and then you need to create the UTCI index out of that. And I think we realized this quite late. You then have a problem. What are you going to take as your index? Is it the core temperature, skin temperature, sweat rate, etc.? So just to look at these, sorry, I've jumped ahead a bit. So these are climate data from meteorological work. Activity we fixed, and I'll show that in a minute. And for the clothing, we used a clothing model of typical clothing. So you could give people the opportunity to put in their own metabolic rates, but then again, you would have, for a certain climate condition, you would have unlimited numbers of UTCIs because it's lots of different metabolic rates. So it was chosen, if you think about forecasting, it was chosen to pick an activity which people would do, going into town, walking through town, walking somewhere. So light work, walking speed 4 kilometers per hour, 135 watts per square meter. And the person, which is of course also really important, this is all calculated for a standard Western European person. Yeah, lots of issues there, potential issues. So that was the metabolic rate. That's fixed. So all across the world, we would put the same value in. And then the question was, well, clothing. So the first suggestion was, we'll give them one type of clothing. But of course, if you're at -40, -50, and you have the same clothing on as at +40, +50, that's utter nonsense. So we decided to actually develop a clothing model. People are assumed to adjust clothing according to the outdoor climate, but within a limited range. So in the summer, the minimum was shorts and shirts. So in terms of decency, we thought that was acceptable, so not the bikinis as I've seen at the beach here. And in the winter, 2 to 3 layers of winter clothing. We looked then for studies of behavior, clothing behavior, and brought together those data. So on the y-axis here, it's intrinsic clothing insulation, but don't worry too much about that. So this is the insulation of the clothing. This is the same thing in a different unit here on this side. Ambient temperature, and these were lots of field observations where people just looked at people passing by and tried to come up with what are they wearing. And in some cases, they were stopped and had, of course, if you have winter clothing, 3 layers, you need to stop them and ask, what have you on under there? So that would be, you could represent this with ambient temperature versus the clothing, so that would be this as a model. But there were some complications or issues to think of. There is a required clothing insulation standard, IREC, and if you use that, that would look like this. That only starts here, I think, about 5 degrees Celsius, and this would be the required clothing according to that standard. So this suggests that people do not wear enough clothing. So this is a model for people who go out, but no, they're not going to go out for 2 days. Yeah, they leave their house, go to work, etc. So we looked for up to 2 hours of exposure as an idea. Lower limit down here. So if it gets hotter, it stays at this value. And in extreme cold, we had input from the Canadians. When it's below -25, they said, well, people definitely add more specialist or more clothing. So we did that as well. So this is the clothing model again. So the blue dots here, that's the same curve up to here as you've seen in the previous slide. And this is the extra increase for extreme cold that we arbitrarily added. So it's lots of arbitrary decisions in this. Then when you have clothing and it starts to blow, the wind starts to blow, your insulation will drop of the clothing. So we had, based on research of our lab, we had models for that. So depending on the wind speed, I've got the 3 meters, 15 meters per second, 30 meters per second based versus almost 0 meters per second. You see the insulation drops. So that's also in the clothing model. So when you put in your temperature and wind speed, etc., this is how it collects, how it calculates the clothing insulation. But there's 2 things. You have overall body clothing insulation, but also different body parts, because this is a model which has a head, feet, legs, etc. So you need to know how the clothing is distributed. So you get some data here. When are people wearing a hat? No hats here above 20 degrees, or let's say 10, but then you see the increases. So limited data sets, but also common sense. When are people start to wear gloves? So no gloves here, but then the colder it gets, of course, the more gloves people are wearing, and the thicker gloves we have. Lower legs, at some point people start to wear shorts, so there's nothing on the lower legs. So that's the way that was approached. So then we wanted to create the UTC or calculate all the combinations. So we did runs for combinations of -50 to +50, mean radiant temperature, -30 to +70 as a mean radiant temperature difference from air temperature, wind speed range 0.5 to 10 to 30 meters per second. And keep in mind, this is the model was developed for using meteorological data. So it's the wind speed at 10 meters high, but don't worry, it's in the model, it's corrected for the height of the person. So if you have a wind speed you measure at the height of the person, unfortunately you have to bring it first to 10 meters for the model to come back. And then humidity in lots of different steps. Below 0, we reduced the number of steps because humidity becomes less important, and that was over 100,000 conditions to calculate. So physiological heat strain, temperature, core temperature, skin temperature, etc. which variable to use for the index? That was the question we came with, as I said just earlier. And there you have some problems. So skin temperature, and this is very schematic, and you can criticize me. I just drew this freehand just to illustrate the issue. In a wide range, your skin temperature will be quite similar because you add more clothing when you get colder. Then at some point it rises in the heat and it goes down in the cold. But remember, we had to have unique values for each. So here in this range, you can't really use the skin temperature as a good indicator for the climate. Core temperature has something similar with a flat area in the thermoneutral zone. Sweating, nothing at low temperatures, and this. So a single physiological variable does not provide a unique index, but we need a unique index. So this is work which Peter Brode worked a lot on, and he used principal component analysis of all physiological responses to come up with a combined index which uses a lot of these different physiological parameters. So it includes into one-dimensional response, rectal temperature, mean skin temperature, face skin temperature, skin blood flow, sweat rate, skin wetness, shivering heat genesis after 30 minutes and after 120 minutes, and they're all combined into a single heat strain response value. That's the idea. So then in terms of the definition of UTCI as an index, we talk about a UTCI equivalent temperature, which is the equivalent temperature of an actual thermal condition is the air temperature of the reference condition causing the same dynamic physiological response. So that combination of all those values is what I call the dynamic physiological response. So let's try to explain that a bit more. So for all the temperatures we wanted to look at, we calculated UTCI based on the model for the reference condition, which was a fixed walking speed, 2-hour exposure duration, mean radiant temperature was the same as air temperature, wind speed, half a meter per second, humidity at 50%, except if it went to very high temperatures, then it's unusual to be above 50%, so we limited it to 20 hectopascals. So everything is fixed except air temperature. So that's all the calculations we did, and those are the UTCI reference temperatures. All the physiological responses are integrated in this one-dimensional reference response, and what you get then is the following. So these are all these reference values for different temperatures that we calculate, and then we take the actual condition and put in the real temperature, the real humidity, the real wind speed, etc., into the model, and that calculates a UTCI, a value here. No, I have to go back a step. So we then take the actual temperature for that condition, which is here. So that's this temperature. And then we look what reference value would give us the same thermal strain as this condition. So that's the horizontal line. So the first thing is we have the actual ambient temperature of our condition we look at. Then we have the strain level of that condition, which is this value. And then we move from that value to the reference condition. So it's the same strain. The strain here is exactly the same strain as there. And that gives us our UTCI value. Yeah, so it's a bit of a, always struggle a little bit to explain that, but you've got your real situation, you take the ambient temperature of that, you calculate with the UTCI model what the strain level would be, and then you look to the reference curve and find the point where you have the same strain level on the reference curve as you have in the real condition, and that gives you your UTCI temperature. So this can be higher. So if, let me think to do this. So it can be higher and it can be lower. So let's go with this. I have that in the next one. So this is another example where you have this level of thermal strain. The reference is now on the left, so you move here, and this gives you the UTCI temperature. So the UTCI temperature may be higher or lower than the ambient temperature. So it will be higher if there's sunshine. It could be lower if there's a lot of wind or you're in the night sky, etc. Yeah? So that's the idea about having an UTCI equivalent temperature. Good. Now, the problem is that a lot of people who, especially meteorologists who want to work with this, like I said, want to do this on a global scale, and they want to calculate 10 by 10 kilometer or even narrower grids. And that would just take too much time to run this physiological model for each time for each of the grid point. So for calculation of UTCI in large-scale weather models, computation time would be excessive. To increase speed, model outputs for all possible realistic combinations of ambient temperature, humidity, mean radiant temperature, and wind are generated. So that's the matrix of four-dimensional matrix of all possible combinations of temperature, humidity, radiation, and wind. They're all calculated, and they're brought together in a big database. And so that means if you then come up with a new condition, you can just look up that condition in your database, so in the lookup table. But as there's more than 100,000 points in that table, that still can take quite a bit of time. So a lookup table with interpolation, so if you have 22 degrees, but it might not have, it might have 21 and 23 degrees for that, you can interpolate between them. And this is the most accurate, but very seldom, in my experience, used way of looking up the UTCI value. Now, Peter Broder also came up with a regression function for it, which is a very, very long equation, but of course you only push that once into Excel or whatever you use, and then you never see that anymore. Unfortunately, if you want to capture that whole database into one regression equation, even if I forgot how many parameters there are in there, there will be some areas where this goes a bit nuts. And for example, at very high wind speeds, you get deviations between these two of like 6 degrees Celsius, which I personally don't like. So if you have the computer power, work with the interpolation, otherwise use the regression function. And you can get this equation and database right there. So look at the whole package. So we measure all our meteorological input. We have a clothing model based on ambient temperature that indicates how much clothing people are wearing. That all goes, and you have the metabolic rate of walking, that all goes into the model. You then calculate the actual condition, you bring it to the reference condition, that gives you your UTCI value, and you can then, if you want to, compare it to this list of areas: extreme heat stress, very strong heat stress, strong heat stress. And to be honest, when Ollie asked me to do this talk, I hadn't really thought about this last bit much, because I've never used that last bit myself. But then if you go to the literature, people of course are using it because it's there. And my gut feeling is that was done quite far at the end, and very arbitrarily, like many other choices, we came up with these different categories. Not out of air, we did think about this. So this is the decision ruling for the categories, but how these are translated in the categories, I think, was more like a shared expert view than there is a direct equation or whatever. So to give you, it's a bit small. So if I take you here at the top, so if you go from to the moderate heat stress, average sweat rate above 100 grams, steep increase in skin wetness, occurrence of sweating at 30 minutes, change of slope versus effect, ET in mean skin temperature, etc. So there's physiological criteria which we felt fit in that zone. If we then go up, and let's say we take this one here, which is the very strong heat stress, increase in rectal temperature at 30 minutes, so very fast increase, core to skin temperature gradient less than 1 degree after 30 minutes. If it would be more than 1 degree, it would go in the top category. So there's, as I said here, it looks at thermoregulatory responses, vasodilation, vasoconstriction, sweating and shivering, and looking at exceeding limit values. But like I say, in some ways, I think I would like people to look at this a lot more. Yeah? At the time it was produced, and I think it was a very good effort, and there was a lot of experts around the table looking at this, but it's not like afterwards there was a lot of validation done to see whether that matches. So one issue with this scale is this is not yet proven to be a linear ratio scale. So tricky to do time level integration. I came across a paper where people, for example, said you take the amount of hours that people have strong heat stress, then you take the very strong heat stress, you give that a weighting of 2, and you give this a weighting of 3, and you combine them all into a certain level of heat stress, which is a really good idea, I think, but we don't have evidence yet that this is a linear scale that you can use in this way. But maybe it is. Yeah? And that's where a lot of these things that I've seen, I wouldn't want to discourage people to use it in certain ways, but always keep in mind you may be the first person to do it, so think really hard about the validity. I also have seen it as used as a fields-like index, and again, going back through this after all these years, I did find there is indeed a dynamic thermal sensation in here, which is generated by the Fiala model, but UTCI was never developed as a fields-like index. It's a thermal strain, equivalent thermal strain index, and that's quite different. So again, you have to be quite careful with that. So when we produced this, and there was a bunch of publications on this, I think roughly in 2012, that all the members of the committee wrote for the different aspects. Has it been used? And yes, I was always quite surprised, especially in the last couple of years. So you see this is between 250 and 300 publications in 2025, which have UTCI either in the title or in the abstract. So that's a good indication that it's been used a lot. You can, of course, do word clouds with this. So the first one wasn't that exciting, comfort, 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 outdoor, and things like this. So I took out comfort. So this is about all those papers brought together and then put in a word cloud. If you take comfort and outdoor out, you get this, which already diversifies us a bit. But you see applications here. But then I thought, well, let's see what AI can tell me about this, because I'm not a big AI aficionado, how you call that. But let's try it. And actually, so all those papers put in into the AI system, and I asked it, divide these papers in 6 categories. And what categories do we get? And so far, when I took the effort to use AI, I've been quite impressed with what it can do. Also been impressed how things can go wrong quite easily if you use it in the wrong way. So if you look at those, I think it was 1,300 or something papers. So around 500 titles were related to urban morphology, design optimization and simulation. So these are, a lot of these are indeed outdoor architecture, shade generation and things. There's a couple of others. Urban microclimate and heat mitigation strategies is similar. The really important one for me, thermal comfort indicators, methods and data sets. Of course, validations would be in here, so that needs, I really want to go back at some point and actually look at those papers in more detail. Health impacts, vulnerability, climate change trends and projections, behavior perception, and mobility usage. So quite a big spread over different topics. These are some examples, but I'll skip those. So some applications of UTCI. So as I said before, a lot of people use it to look at the impact of climate change and look at how you get these world maps, and you see the change of the world map pre and post. We did a project Heat Shield, which was a European Union project for workers working in the heat and what will be the impact of climate change on them. And I'm going to use that as an example of application of UTCI. So how does climate change affect the physical, or I prefer nowadays to say physiological work capacity? And the experiment was actually quite simple, and James Malcolm, together with Josh Foster, were the main people who were doing all this work in the climatic chamber. Endless work, but very unusual. We had the funding for 982 exposures, which is really unusual to have. It's about 4 years, I think, James, isn't it, of work. We did exposures of 1 hour, because ideally you want to do full days, but of course you can't afford all that. So we first did a lot of exposures, I think 600 or 700 and something for just 1 hour. Then we repeated what does it mean if people do this a full day. healthy young males. So with all the money we had, there was no money for unacclimatized versus acclimatized females, aging, etc. And we had temperatures 15 to 50 degrees Celsius, humidities 20 to 80% in steppes, sunshine, solar radiation, 0 or 800 watts per square meter, and then we had wind speed 0.2 or 3.5 meters per second wind. You see the setup here. In this case, the radiation comes from the back, so not from on the head, but in the back, with a coverall or with just shorts. This is the setup when we had wind, with the little wind tunnel that we had and sucked air through. So what was special about this is all these experiments were done with the people having a heart rate of 130 beats per minute, and I'll show you a graph how that works. And the measure that we used to evaluate things was the energy generated above resting. Yeah? So when people are doing this work, they generate energy, metabolic rate, and how much they can generate above just sitting still, that's what we said, that's your work output, physiological work output. So how does this look? So this is in a cool environment. This treadmill comes up to speed, and then you have a heart rate of 130, and the treadmill regulates that by, it brings up the speed here, that's close to 6 meters per second, and then it adjusts the grade, and you see a little bit of drop of grade happens because people warm up a little bit, and that means you have to put more blood to the skin, which is blood you can't use for the work. That's clearer in the heat. Same thing, heart rate goes to 130, and just to say the 130 is quite a heavy work rate, and the World Health Organization classifies that as the edge between moderate and heavy work. So that's why we went into that region. And also when we did try this at 120 beats per minute, people had to stop very quickly with any activity in the climate, so we were worried we wouldn't measure anything. So here in the heat, speed goes up to the usual way, the grade goes up, but then people start to heat up, and again when they heat up, your heart will pump more blood to your skin for cooling. That's blood that doesn't go to the muscle, so you have to slow down, yeah, because the muscles get less blood. And that's what you see here. So first the grade comes down, at some point your grade of the treadmill is back to 0, and then even the speed comes down. And in the extreme cases, probably after 10 minutes, people would just have to stop, because even at rest, their heart rate would go up and up. So that's the idea. Again, another picture of how it was in the chamber. And so we would calculate the total energy generated above resting from these value of speed and grade. So let's say at 15 degrees Celsius, which was our reference, you had 1772. At 35 degrees, 50%, you had 1143. And that means our physical or physiological work capacity is down to 65%. Very, very simple approach. And if you're interested, I just list these. So we did experiments on temperature and humidity combinations, wind combinations, radiation, the whole day shift, and then we integrated all of these into one paper where we have all the equations combined. So if we first look at simple one parameter models, air temperature. So sorry, let me explain this. So we've got air temperature on this axis, and on this axis we have the labor capacity loss in the percentage of cool. So the cool combination of 15 degrees Celsius, the energy generated there is 100%. Yeah, that's our reference. And then we make it warmer, and people have to slow down. So the value here is the loss of work capacity. So if you reach 100, you can't do anything anymore. Now, if we have in this, we have data for temperature, different humidities, different wind speeds, sunshine and no sunshine. So it's again the four-dimensional space. And if you would use air temperature as the parameter, you see you would have huge ranges of outcomes here, which is not usable. Yeah, so that's the thing. Ambient vapor pressure, similar. There is a relation, but it's very, very weak and huge spread. Relative humidity, there's nothing, which is, of course, what I love, because relative humidity without temperature is meaningless. Wet bulb temperature, it actually is already a bit more, because that has temperature and humidity combined in it. But now let's look at some of the climate indices for this. Again, air temperature as a reference in the bottom right-hand corner. And we have different ones here: heat index, MPAT, natural wet bulb, already had that before. And here we have the more or less the competitors, WBGT and UTCI. And you see suddenly all those points have moved closer together, and we have really, I would say, given the variety here, a really good model of describing this loss in work capacity. And you can see that we went quite extreme. So this is in air temperature up to 50 degrees Celsius. We didn't do 50 degrees Celsius with high humidity because that would just be a killer. But desert conditions, 50 degrees Celsius, 20% humidity is the type of thing. So this is an example of an application. And just to bring in these classifications here, so I copied the colors across here, and I did that this morning, so I haven't looked at it in all detail. But what you see, green, indeed, there's hardly any drop. Then we get to moderate, and there's a drop of maybe 10 to 20%. And then here, when we move from very strong to extreme heat, we more or less have 50 to 60% work capacity loss. And that probably is, if you lose 56% of your work capacity, that's probably quite an extreme situation. So I just lifted out these two, UTCI and WBGT. And actually, if you look at statistics, they're very close together. So the descriptive predictive power of UTCI and WBGT looks similar. So why do all this work with this physiological model? Why? What discriminates them? Why use a complex UTCI over a simple WBGT? And this worried me a lot when we first found this, but fortunately, we did find some differences. And just to try to explain these, if you have this instrument and blow wind over it, your WBGT will always come down. No matter what the temperature is, it will come down. And that's not what happens to a human. If I put you in 60 degrees Celsius, or in your hot air oven, when you switch to hot air circulation on, everything cooks much quicker. So if you have a climate of above 50 degrees Celsius, you add wind, it makes things worse. It helps you evaporate sweat, depending on the humidity, but it will push in a lot of heat. So this will always get better if you add wind, and that's not what we found in the data. So here in this slide you have labor capacity change, and just two examples that we looked at: very hot dry and hot humid. And what we see here, the labor capacity in the very hot dry, when we switched on the wind, so this is the difference between no wind and wind. When we switched on wind, it dropped by a further 14%. And the UTCI went up by 2 degrees Celsius. So things were worse according to the UTCI, but also worse in labor capacity. Here, in the hot humid, so this was very hot dry, now we'll go to hot humid, we actually improved work capacity, and UTCI came down by 2 degrees Celsius. So that was consistent with it, but WBGT would have gone down in both cases. So when we then looked at the data, and specifically looked at the data about where wind was present, we could clearly see that UTCI captured this, and it's a physiological response, because if you add wind, for example, in a very hot, dry climate, at some point you sweat maybe 1 liter, but that evaporates easy without wind. If you're at 40 degrees, 10% humidity in the desert, and if you switch on the wind, not more will evaporate, but you will be pushing more heat in. So those kinds of issues were not covered by WBGT. Then there's a couple of others, and I only looked up a few, and actually Ollie sent me this one, I think. This was in The Economist, looking at heat waves, and they produced a graph what they said maximal feels-like temperature, which is, like I said, incorrect. But then they looked at the distribution over the different categories, with Europe, of course, having very little in the extreme categories, India more, and I actually struggled to figure out whether, I assume this is a cumulative graph, but I couldn't really find that information. So that's, in principle, a good idea to use, but they talked about vulnerable population. And the big question with this index is, which I have here, So if you're going to look at vulnerable population, which might be older people, which might be people with disabilities, you have two choices. You will either have to change the model, which we lock down, so problem, or you have to adjust the limit values. So you would have to change the color scale, for example, for the different populations. And again, we don't have research on that, so please. Good news in that respect. Peter Brode, again, with colleagues, has gotten a project for the German military, where he specifically is asked, can you apply UTCI to military applications? High metabolic rate, more clothing, backpacks, things like this. So there, well, that's the German title of a publication. Translated, Judging Thermal Risks, Project on Expansion of UTCI with Military-Specific Activities, Clothing, and Individual Variability. So that's, I think, a first step where it's expanded into those things. The risk is, of course, that you produce multiple UTCI versions, but I think as long as you define it, this one is exactly only for this application, I think that should work, and it's a very interesting project. I'll skip this one, but the idea is, can you look at again, at vulnerable groups, but given that we'll skip this one. There's also cases, and in the literature we'll find more. The work capacity one is where UTCI worked really well. There's also situations where it doesn't work well. And there's a number of people, in this example, this is Sebastian Ressenes group, and this is Lars Niebuhr's group, who have tried to apply this to athletes and top athletes in international competitions. And they find, in this example, for example, they looked at exertional heat stroke occurrence against WBGT, so they didn't do it against UTCI, but I don't expect too much difference. And so this is the occurrence, 1, 2, 3, 4 at each condition for different races. And you see, well, that's the curve, but that doesn't represent what's really happening. So for these very high metabolic rates with WBGT, they didn't find a good relation. And I would expect UTCI would struggle with that as well if you don't adjust the metabolic rate. So conclusions. We're very happy UTCI is taken up well by the scientific community, but maybe on occasion be used outside its original remit. So always try to think that choices were made at the time, and does that actually match with what you want to do? And if it doesn't match, you can still use it, but think about it. That's the thing. And you might be creating data that we can use to expand the application. So this may be okay, but validation is needed. It allows climate comparisons spatially and temporally on the basis of physiological heat strain. It does not yet have the long history of WBGT. WBGT 1950s. Loads and loads of work done, especially probably before 1980, 1985, when most countries started to deregulate their legal criteria in their laws. Because if you go back further, WBGT limit values would be in the laws. Then everybody took them out and felt that was the industry had to solve this. But there's a huge amount of work done there which hasn't been done yet on UTCI. Acclimatization effects is one that I'm really keen on doing for the work capacity one, for example. Clothing correction factors, etc. Originally developed as an outdoor index, another thing to keep in mind. But has been used inside. Of course, then your radiation is not going to be so much, show that much variability. In physical work capacity estimation, it shows improvements compared to WBGT for specific condition. It has potential for evaluating specific vulnerable groups, but this needs further validation. And this might require to go back to the original model parameters, or using different interpretation values of the outcome. Good, thank you very much.
Before we get into that, I'll just kind of finish off with a couple of take-home messages from your talk, George, so that I took home anyway. The first thing is the way in which we define UTCI. I think a lot of people struggle with that. And so, as you mentioned, it's not a feels-like index, it's a physiologically-like index.
Yeah.
Maybe that's a good way of thinking about it. So that's maybe one thing that, to go from this. And the other thing as well, which is I know that we've talked about before, and I've talked to a lot of other people about, is the caution with which people should use those risk categories that are associated with given bands of UTCI for different types of populations that are outside the current model. So the current model is focused on males only, is that right? So male only, young, fit, healthy people, and with a given physical activity level as well. So if we're thinking about that from the perspective of utilising this tool, if we've got people doing different levels of physical activity, those risk bands should probably slip to a lower UTCI. If we're applying it for older individuals, people with chronic diseases, we again should be slipping down those bands to a lower critical UTCI for a given level of risk. However, we don't know for sure where those should sit yet. So that's a really good opportunity for future research and collaboration among different groups. So just wanted to share those comments.
If I can jump in very briefly, so you focused on a male, that's true.
Yeah.
But if you look at the literature in the thermal physiology area, that if you have a male or a female of similar fitness, there's very little difference.
Yeah.
But of course, on a population basis, there is a difference. Yeah. So you have to consider that.
Absolutely. Yeah, just because we're saying that there are not that many data on female doesn't mean that there's automatically going to be a difference, because often there is a temptation to assume there's going to be big differences when that's not actually the case. Okay, so questions? Does anybody have one? Yes.
Thank you so much. Heaps of questions, but very practical one. I noticed a lot of the time UTCI brackets C, which I guess centigrade, degrees Celsius. So is that a proxy? What was I didn't quite understand what the brackets Celsius was for.
Yeah, so that's the units in which we express, and that's because we use ambient temperature for the comparison. So we look at the ambient temperature in the real situation and then the same level of thermal stress in the reference condition, and they are both expressed in ambient temperature. So that's why the unit is used as degrees Celsius, but could be converted, but that's straightforward.
So can you give us a quick example? So let's say the humidity's higher, it's sunny, and then you get a UTCI of 39 degrees Celsius. So the physiological strain is the equivalent of the air temperature being 39 degrees Celsius, but really it's 30 degrees Celsius, but humidity's higher and it's sunny. Is that?
Yes, so yes, if you would get a value of 39, is that the physiological strain is equivalent to the one you would have at 39 with 50% relative humidity, with specific airspeed in the reference and specific clothing that's provided by the model. Yeah.
It's interesting because when it comes to the feels like index, everybody's totally fine with that, right? Say, oh, it's 32 degrees Celsius today, and, oh, but it feels like it's 39 degrees Celsius.
Yeah.
And in a sense, it's the same thing with UTCI-ish,
yeah.
But instead of it being feels like, it's physiologically like.
Yeah. So one problem we came across with having lots of people from different parts of the world in the committee is the feels like is different whether you are coming from a desert country or from a jungle country. Because we took 50% as a reference. So in the desert country, the UTCI for a certain condition will be worse than the people maybe experience. Yeah, because we move it to 50%, so we push up for the reference, we push up the humidity, and in the jungle it's the other way around. So that was one we couldn't solve really. If you want to have a universal index, you apply across the world. So that's why in the end we just went for the 50%. But there were issues with people from different countries, like that's going to feel awkward. So that's why it shouldn't be interpreted as a feels like, but as a physiological strain like. Well, that's at least my view. Physiological like.
I came with that yesterday. Any other questions?
Well, unlikely, I've noticed a lot of the news reports telling us what temperature it is, and it feels like, where are they getting those figures from? It feels like.
Yeah, so yes, that's what you indeed find in news broadcast. And now his name evades me.
Stedman.
Yeah, Stedman. So Statman, an Australian researcher, which I'm not sure he's still alive, but he worked a long time on this fields-like aspect, and he has done a lot of work, which is really, if you go into the detail, it's a tremendous amount of work on this. But it was a different purpose. And the problem that happened, I think, because he also has a similar complex model with which he calculates this, but then the weather services came up and created regression models that represented his data and simplified it more or less. As far as I can see, the Americans, they simplified it in just a temperature and humidity index, ignoring a lot of the other ones. And like I said, Statman did a lot of really good research, but one problem I always had with his research, because he would send me updates every couple of months how he was developing his model, there was always a new model. And you can understand that as a researcher, you want to improve things, but of course for people that are going to apply it, that's difficult, because which version are you going to use? And if that's 4 or 5 steps different from last year's version, it gets very difficult to get consistency.
Okay, so we've got a couple of additional questions, so these are probably the last 2 that we'll ask online. As mentioned, that the strain model is locked, so that I guess the Fiala model is locked, and a black box model. If someone wants to improve the model by putting clothing model or other parameters from a regional country, how should they proceed? So people who want to contribute to improving this UTCI model, given that the Fiala model is locked, how can we go about doing that? Great question.
Straightforward, talk to Dusan Fiala. I've done a lot of projects with him since this, and using his model in different applications. So it depends very much, I think, whether it's a commercial application or not, how willing he would be to open up. But I think that's the only way, is talk to the originator.
So Dusan's based in Germany. Where
yes, he's in Germany. Yeah.
Do you know which university?
He's actually he opened a private consultancy, I think, a number of years ago. Yeah, but you will find him quite easily if you look up Fiala model, and I will have the email.
Or you can get in touch with George.
Yeah.
Then the final question. Are you saying that people from a desert climate feel hotter in high humidity but are under no more physiological stress? So is there no acclimatization to humidity?
I'm not saying that.
Okay. maybe Rosalie is asking you what you are saying.
Yeah, so I think what I tried to say about these people from desert countries, etc., if they use this model, because the reference condition is at 50%, they might intuitively think that's the wrong direction, but it's still equivalent physiological strain as it would be in 50% humidity. Now the question is whether people would feel, from the desert, would feel better in a hot, humid climate, etc., which they could cope better with. There's been a lot of research. I think the first papers on that were probably 30 years ago. Barbara Griffan did some papers. People have been doing cross-acclimatization, so acclimatizing people to hot, warm, humid, and then putting them in hot, dry, and see how this is. And I wouldn't dare to give a conclusion what the current state of the art is on that one, but I know there's a lot of work done in the last 30 years on that.
Okay, well, I said I was going to ask only 2 more questions, but Daniel just popped one in, so I'm going to ask you this one as well. Question on the effect humidity has on the UTCI model adjusted for tropical dwelling populations adapted to high humidity. So does the model have capacity for these regional heat adaptations? So I guess this is a wider question about how does heat acclimatization, which is a physiological phenomenon, how does that, or does it not, get integrated into the UTCI model as it stands at the moment?
Yeah. So again, that was a choice because it would be adding another parameter. The question is, how long have people been in this location? And there are models which include this, so people adapt to it. We decided not to include it because anything more complex than what we already have, we felt would not be useful for a general, simple population application. But definitely, I think the current Fiala model has information on that in it. When I showed my work from 2001, the publication, there was an acclimatization factor in there as well. So it was like a curve which gave you the number of days in the heat and would then adjust sweat parameters, skin blood flow parameters based on how long people had been exposed to the heat.
Okay, great. And so just to be a clear conclusion then, so at the moment, the assumption is that the person in the UTCI model is not heat acclimatized. Is that correct?
I would have to check
George,
on that one,
no,
but
no, no, so you can say whatever you
my
like.
gut feeling is that it's not.
Not,
Yes.
okay.
So it would be an initial exposure.
Yeah.
So, for example, somebody in Western Europe who suddenly has a very hot day,
Yeah.
or vice versa.
And I think Caroline Broderick and I talk a lot about this, about risk management, and it would make sense to assume that they're not acclimatized, because then you're not under-protecting people, if anything, you're
Yeah.
over-protecting. So from a
Yeah.
risk management perspective, that probably makes a lot of sense. Okay, we'll wrap it up there. George, thank you so much for a tour de force